Good afternoon. Hope that everything is fine with you. And we shall continue considering the theory of elasticity. You remember that after some calculations and some definitions, we introduced the stress tensor, sigma, that is defined as a linear combination of the entries of the strain tensor epsilon. Apart from the tensor appearance of this expression, we observed yesterday that this is the generalization of Hooke's law. Hooke's law was stated, as you remember, it is written below, by the end of 1600, and substantially the first expression of it was that the tension was proportional to the force. It is curious that at the time of in which Hooke decided to make his discovery public, there was no copyright. Okay, so people typically copied results from one another. So scientists liked to keep the results hidden somewhat in order to be able to reveal them at the proper time, okay? So what Hooke decided to do was revealing his law by an impossible anagram. The anagram is indicated at the bottom of the page. In essence, he translated the law into Latin, ut tensio sic vis, that means like tension like the force, or same as the force. Vis is force in Latin. And then he simply scrambled or shuffled the letters of this sentence and put them in alphabetical order. Okay, so he put this impossible anagram together, and then he kept it secret for 2 years until in 1678 he revealed the meaning of the anagram. So if you keep the tensor form of the law, you must express the law in the most general form, that is the one shown here, okay? By the way, this law is a general definition that also applies to the dynamic case. In fact, sigma in the second equation that is visible in this page is actually the same sigma as above, okay? But in many situations, we don't have any time dependence of the different quantities. We have some equilibrium situation in which the material is subjected to forces, so it undergoes a deformation, but after the application of the forces is completed, then nothing moves anymore. So the law also applies to the equilibrium case, and in many situations later on we shall examine equilibrium cases. So we shall come back to the more general dynamic equations at the end of the analysis of elasticity, but from now on, we consider only the static cases. And now I have to change the slide in order to go back to the slide that we were discussing yesterday at the end of the last hour. So we were here. This, as you remember, is just a very simple one-dimensional application of Hooke's law. We have a cylindrical piece of material that is elongated in the vertical direction, and the length of the unperturbed case is L0. We apply a force on the upper face while the lower face is kept fixed, and there is an elongation delta L0 of the bar. The stress in this case has only one component, that is the vertical one, and this component is given, of course, by the force F divided by the area A0 of the cross section. And the component of the strain tensor epsilon is delta L0 over L0. Also, the ratio between stress and strain is called the Young modulus. You remember that due to the units of the different quantities indicated here, the units of the Young modulus are those of a Pascal. Actually, if you remember, if you have some concepts of elasticity, you know that this is not just the only effect, because when you pull a piece of material, so you make it longer, since the volume, the original volume must be conserved, you expect that the bar would also become a little bit thinner, okay? In fact, it is so. And there is another parameter that we shall see very soon, that is the Poisson coefficient that describes the thinning of the bar. Anyhow, we continue. I resume here the list of hypotheses that we already started examining. We always consider a linear response. So the relations between strain, stress, and so on are always linear. We never consider higher order terms, which implies that the deformations of the material that we can consider are small deformation, but this is reasonable for many applications. The other thing is that from now on, and for a while, we shall assume that the system that we are considering is in the equilibrium condition. That is, there are forces applied onto the system or onto the body that we are investigating. But these forces do not depend on time, and possible transients that occur at the time of application of the forces have finished. So everything is static, okay? But because of this, the body is not accelerating, and also the body has no rotation. not rotating around any axis or any point. So that means that in equilibrium, all forces that are applied onto the body compensate each other in the sense that the resultant force must be equal to zero, but also the resultant moment must also be zero. Okay. Since all forces combine to zero and all moments also combine to zero, that means that we expect that there are relations between the components of these forces. Okay. You also remember that we consider, instead of the forces, we consider the forces per unit area, that is the stresses. So we shall examine the relations among the components of the stress. Another hypothesis that we already discussed is that the linear dimensions of the body that we are considering are large enough to consider the body as continuous. So we do not care anymore of the atomic structure of the body. We treat it as if it was a continuous body. Typical example, you remember the lattice constant of silicon is about 5.4 angstroms. Whereas when we consider semiconductor devices used as microelectromechanical systems, like the acronym is MEMS, as you know, the minimum extension of the device is 50 nanometers, okay, which is much larger than the lattice constant. We always consider the case in which the forces are applied over the surfaces, over the external surfaces of the body. Those are not the only forces, of course. There are also volume forces. The typical example of a volume force is gravity. Gravity is a volume force. It is not applied over the surface of a body. Okay. So we also must consider what is the relative importance of volume forces like gravity and surface forces. And we can see easily that when the size of a structure becomes smaller and smaller, the surface forces become more relevant than the volume forces. Typical example, if you take a cubic block of material whose side is 1 meter, the external surface will be 6 square meters and the volume will be 1 cubic meter. So the ratio between surface and volume is 6 meters to the minus 1. If you take 1 centimeter, of course, the surface area will be 6 square centimeters, and the volume will be 1 cubic centimeter. So the ratio will be 6 centimeters to the minus 1, which is 600 times larger than the former case, okay? So, which is reasonable, okay? Because when we make something smaller and smaller, the volume decreases with the cube of the radius and the surface decreases with the square of the radius. So from now on, we consider pieces of material of cubic type. It is not very important that they be cubic. They could be prismatic. So the size along the 3 direction could be different, okay? A1, A2, A3 are the areas of the faces. A1 is the face that is forward, A2 the one on the right and left, and A3 top and bottom. Okay, and the forces applied at the surfaces, that could be of the type of pressure or bending or twisting, condensate into the stress tensor. Okay, so consider any face of the prism and consider that on this face we have a force. You remember, in general, we have both a force and a torque. But when we make the block smaller and smaller, the torque becomes not relevant. Okay, so we are considering only the force. On each face, there is a force acting, and this force is not necessarily normal to the face. Okay, so in this figure, what you see is just the normal component to each face, but then in the next figure, we shall see the parallel components to the face. Okay, so for each face, we have a general force applied. We decompose the force into the normal component that is visible in this figure here and into the parallel component. We shall examine the parallel component next. The component normal to the face is divided by the area of the face. So if you take the face to the right, the force applied to it is F2. When we divide it by the area A2, we obtain the so-called normal or axial stress of that face. So we call it sigma 2, okay, where the first index refers to the face, because the face is A2. And the second index refers to the orientation of the axis to which the force is parallel. So the axis is the axis number 2, because we are considering F2, so we have sigma 2, okay? Of course, we could swap the two indices and change the definition, but nothing would change. So we have 3 normal stresses, and then of course we have 3 more on the opposite faces, okay? And in order to impose the equilibrium condition, we must find out the relations among these components. Now we go to examine the components parallel to the faces. So in this figure, what you see is that we are considering only face A1, that is the face that is in front, okay, of the prism. And all 3 components are drawn in the figure. So F1, as in the previous page, is the component of the force normal to A1. F2 is the component that belongs to the plane of the face and is parallel to the second coordinate axis, x2. And finally, F3 is the component that still belongs to the plane of the face A1 and is parallel to the third coordinate axis, okay? So then we already have defined sigma 1, 1, that is F1 over A1. Then we must define the other two that are F2 over the area A1 and F3 over the area A1. And of course, these will have two different indices, sigma 3,1 and sigma 2,1. Okay, so actually the index of the phase comes second, and the indices of the axis come first, but it doesn't really matter because we shall see in a minute that this tensor sigma is symmetric. Okay. Now we have to impose the equilibrium condition. So we must impose that the block of material has no acceleration. That means that all components of the forces must compensate each other. So if we start with the normal component of the forces, we must state that those that are applied to opposite faces must be equal and opposite to each other. So in the upper part of the figure, the component Fy that points to the left must be equal and opposite to Fy that points to the right. Okay, this is intuitive. And the same is for the forces Fx and Fz normal to the other pairs of faces. Okay, here they are called with the XYZ indications instead of 1, 2, 3 as was done before, but it is the same. Now we have to consider the parallel components, and the parallel components can be discussed using the lower part of the figure. Sorry. Is it still visible? Okay. Now let's consider, for instance, a component that is visible on the right part of the block and is called Fz, and assume that Fz points upwards. Okay. On the other face, on the opposite face, there must be another component Fz that is equal in modulus and points downward. So if that happens, and this does happen, Fz on the right compensates Fz on the left as forces, but not as moments. Okay. So they will not impose a translational motion to the block, because the component that points up is exactly equal to the component that points down. But these two components will impose a rotation of the block around the center, because obviously there is a moment of the force to the left that is Fz times the radius of the block in the y direction, Ly. And then we have an identical contribution from the other side. So we have 2 times Ly Fz, okay? So this condition is not correct, because we see that in equilibrium there is no rotation of the block. So we must enter into the discussion also the other component, the other parallel components of stress, and this is visible here. We must remember that besides the components Fz, we also have the components Fy, that are those that are parallel to the upper and lower face. Okay. So Fy on top must be equal and opposite to Fy on bottom in order not to have any translation of the body. But the moment produced by the two components Fy must exactly balance the moment produced by the original two components Fz that we discussed in the previous slide. Okay? So if we impose that the global moment, of course, this is a moment that is related to the x-axis that in this figure is normal to the page. So we must impose that 2 times Ly Fz minus 2 times Lz Fy be 0. Okay? Then we must divide that relation by the area because we want to go from forces to stresses, okay? And we obtain that the non-diagonal components of the stress must be symmetric, as we anticipate. That is, sigma of ij must be equal to sigma ji, okay? Some of you may argue that this reasoning seems to work only for a cubic block, okay? What happens if we have a block that is non-cubic, so that Ly, Lz, Lx are different from each other? We shall see later that the conclusion is still correct. It doesn't really matter whether the block is cubic or non-cubic, okay? All these moments actually do compensate. So the stress tensor is symmetric. Of course, all indices of the stress tensor go from 1 to 3. So in principle, it is a 3 by 3 tensor with 9 components. But being symmetric, we do not have 9 components that are independent from each other. We have only 6. And they are the diagonal components and either those on the upper part of the tensor or the lower part of the tensor. Okay, so due to symmetry, we have only 6 independent components of the stress tensor. It is usually the tensor is usually manipulated by reordering the components, as you can see in the figure lower left, okay? And the 6 independent elements are rearranged in a vector, okay? So it is a vector that comes from a tensor, okay? It is more convenient to consider it as a vector. Now we repeat some of the considerations very quickly that we already have done yesterday when we have a stress that is axial, that is aligned with one of the coordinate axes, as you can see in this figure, and the stress is such as to extend the block, okay? We have the so-called axial stress. Okay, so we assume that in this figure only F3 is present. When instead we have only force is parallel to the faces, we have the shear stress. Okay, so the deformation is of the type that we have examined. By the way, in this figure, some of the arrows are not very well visible. There is, if you look at the left part of the figure, there is F2 on top, but also F2 at the bottom here. And this translates into this type of the deformation shown in the upper part on the right, F2 here, and there is another F2 that is barely visible here. Instead, the lower part on the right indicates the situation in which we have only F3 that goes up, so it produces a deformation in the vertical direction such that the right face shifts upwards and the left one shifts downwards. Okay, there is also F3 on the left, not visible very well. We are going to skip this figure and also the next figure because they refer to some discussion that we have already done. That is, we always neglect the possibility that besides the deformation, the block of material also undergoes a rigid translation and or a rigid rotation, okay? A rigid translation is the one depicted on the left, and the rigid rotation is the one depicted on the right, okay? Always, these things always occur, but we simply neglect them, okay? We consider only the local deformations of the body. Then at some point we defined, using different symbols, but the concept is the same. We defined the strain tensor. It is the first parenthesis here. The symbols are different because in the other slides, here we have U, but in the other slides we had psi. Okay, but it is the same thing. And the other part is the anti-symmetric tensor that describes the rotations. And this is the one that is neglected. So it was called theta, if you remember. Here it is called omega, but it is the same. From now on, we shall consider only the strain tensor. And the strain tensor is symmetric. So also in this case, out of the 9 components, there are only 6 components that are independent from each other. We also rearrange this as a vector, okay? And the reason is that when eventually we want to describe the relation between strain and stress, you remember this is done using the elastic tensor. We have a simpler representation of this relation. It is a vector equal to a matrix times another vector, okay? You also remember that initially when we introduced the elastic tensor, the total number of components of it was 81. But we have been able easily to reduce it, to reduce the total number of independent components, first to 21, then to 15, and finally, considering the case of a cubic crystal like silicon, for instance, or germanium, down to 3, okay? So the elastic tensor that connects, as you remember, the strain tensor to the stress tensor is a 6x6 tensor having 3 independent components. And there it is. This is it. The symbols are a little bit different because in the other slides, the components of the elastic tensor are called capital phi, okay? Here they are called small b, but the concept is the same. It is a 6x6 matrix. The first block of it is a 3x3 matrix in which the diagonal elements B11 are equal to each other. And the remaining 6 non-diagonal elements are called B12. They are equal to each other but different from B11. The rest of it is made of another block that is purely diagonal, in which the diagonal elements are called B44 and they are equal to each other but different from the rest. And all the rest of the matrix is made of zeros, okay? This is also called the compliance matrix, as you can read on top. And in the typical theory of elasticity, they don't use these symbols, B, neither the symbols capital phi. They use other symbols that are visible below, but they are also mentioned in the next page. Anyhow, the inverse of B11 is called capital E, and this is the Young modulus. The inverse of B44 is called capital G, and it is called the shear modulus. And B12 is called minus Ni over E, where Ni is called the Poisson coefficient. Why the minus? Well, you remember the discussion that if you take a bar and you pull the bar becomes longer, but you expect that the volume of it should be conserved, so that the radius of it should become smaller. So the bar becomes longer but thinner. This is why we have a minus sign in the Poisson coefficient. The definitions are also in the next page. So the matrix that is associated to the elastic tensor is called the compliance matrix. Okay, it is the matrix that multiplied by the stress tensor provides the strain tensor. The inverse of this matrix is called the stiffness matrix. So the stiffness matrix multiplied by the strain tensor provides the vector, provide the stress vector, okay? And the names of the constants are repeated here, the Young modulus, the Poisson coefficient, and the shear modulus. Now, the equations are already discussed, so we don't go through any equation. How do we apply these concepts? Remember, we are talking about microelectronics, okay? So, of course, we must be able to find microelectronic structures in which we can realize mechanical things that can bend, okay, or deform, okay. And essentially there are two of them. One is the cantilever beam, in which you have a structure that is blocked on one side. In this figure, it is blocked on the left side, and can deform due to forces applied on the other side. These forces may be concentrated forces or distributed forces. We may have both types, and we shall see them in a minute. By the way, if you look at the figure of the cantilever, it is now better understood why we always say that we dispose of the rigid rotation or translations. Let me try to expand the figure if possible. I'm not sure I can do it. Okay, assume that you have a little block of material here in this position, okay? This material is deformed with respect to the unperturbed case, okay, because there is a deformation of the material. But this little block here also is down by a significant space with respect to the original position. The elementary block that is at the end of the cantilever beam is down by some distance d, that they may be large, okay? But this shift has no effect on the mechanical properties, on the electrical properties of the little block. It is has simply moved somewhere else in space, okay? So this is why we must eliminate the rigid translations and rotations, okay, and then we calculate only the local deformations of the material. The other structure is the so-called membrane or plate, okay? So in the lower part of the figure, you can see just a cross section, okay? Assume that you started with a wafer of silicon. In fact, you see that the thickness of this structure is about 250 microns. That is the typical thickness of a wafer, okay? Then you have deposited some materials, like the oxide here, and a layer of silicon here. Of course, all the part that is now missing at the beginning was present, okay? So it was a full wafer of silicon. After completing all the depositions on top, with a chemical attack from the bottom, they eliminate a larger part of the wafer, okay? So they realize this excavation from the bottom, so that what they leave out is just the superficial layer of the metal, of the semiconductor, okay? So, of course, the wafer is much wider than this, laterally. There is more wafer than is visible in the figure, okay? But we have a very, very thin layer here in the central region, and of course this is also true in the direction normal to the page, so that if there is a difference of pressure for any reason between the upper and the lower face, this membrane or plate will deform. And through this deformation, we shall be able to measure the force that is, or the difference of forces that is applied from one side to the other of the material. Then how do we exploit the cantilever beams or the plates? Essentially, we may exploit them in at least two ways. One way is that if the cantilever, for instance, is one of the two plates of a capacitor, if the cantilever deforms, then the capacitance of the capacitor will change. And the capacitances are things that we can easily measure. Okay? So if we are able to connect the change in capacitance with the change in the geometry of the capacitor, and then we are also able to connect the change in geometry with the force that has produced the change in geometry, then by measuring the change in capacitance, we measure the force. Okay? Force or other things related to forces. Okay? Another possibility is exploiting the so-called piezoelectricity or piezoelectric effect, in which some materials are, when are subjected to a pressure or a tension, they are able to produce some charge that in turn produces some voltage. So by measuring the voltage, thanks to the piezoelectric effect, we can measure the force that has been applied to the structure. Okay, so now it is 28, so I think we can stop here, and we shall continue on this line in about 10 minutes at 4:40. Okay, so let me put the screen again here. Okay, so now we continue on this line. Considering the case of the cantilever, the figure shows combinations of possible loads that are applied to the cantilever. For instance, P3 is a force that is a so-called concentrated load. So it is a force that is applied on a single position of the cantilever, actually at a distance a from the left end of the cantilever. The left end of the cantilever is blocked, so point A of the cantilever cannot move. At point A, there is no possibility for translations or rotations or anything of the cantilever. So the symbol H sub A and the symbol M sub A with the bar means there is no normal force and no rotation. Okay, no translation and no rotation. Same for RA. Another possible type of load is the so-called distributed load. In this case, we must provide the intensity so that we assume that this distributed load may change only along the horizontal direction, that is along the axis L of the cantilever, and it is not necessarily uniform. For instance, the part of the figure on the right where there are the symbols Q1, Q2. So Q is the symbol here for a force per unit length. And this force per unit length in the example visible in the figure is applied over a length equal to small b of the cantilever, and it is a force per unit length that changes linearly with position from some value Q1 to some other value Q2. Okay? How do we, once the loads applied to the cantilever beam are prescribed, how do we calculate the internal forces like shear forces or normal forces or momenta or moments, sorry, that are present inside the cantilever? The general approach is shown in this figure. For some reason, now the end of the cantilever that is blocked is on the right. Okay, so the orientation of the cantilever is reversed with respect to the other figure, but this really doesn't matter. Okay, so consider that we have a cantilever in which the right end, that is the position B, is blocked, and that on the tip of the cantilever, that is at the left end, there is a concentrated load P that is applied in such a way that it points upwards, okay? How do we determine the internal forces at any position inside the cantilever? This is relatively easy because you remember in dealing with this type of problems, what we do is we remove one part of the cantilever and replace the missing part with the actions that the part that has been removed exerted on the remaining part. So if we want to calculate what happens at some position that has a distance x with respect to A, we simply cut, ideally, the cantilever at position X. We separate it into two parts. And after we have separated the two parts, to each end of the separated parts, we apply a force and a moment such that the action of the force and the moment that we have applied compensates for the part that has been removed. So it is like, instead of being acted upon by the part that has been removed, the part of the cantilever that we are examining is acted upon by a force and the moment. Okay. Now, if you look at the left part, the one that goes from point A to the right for a length equal to x, and we remember we are in the equilibrium condition, so the cantilever has deformed, okay? So it is not a straight structure anymore, but after the deformation has been accomplished, nothing moves anymore. So we are in the equilibrium condition, and the deformation is so small that our reasoning can be based still on the undeformed situation. Okay, so the cantilever, or the left part of the cantilever, cannot accelerate due to the application of the load P, and that implies that there must be a force on the right face of this part, and this force is V, that is vertical, but opposite to P, such that the combination of V and P compensate each other, and the total resulting component is zero. Okay, so the action from the right part of the cantilever on the left part is this vertical force V. Of course, it is a shear force because it is parallel to the face. But this is not enough, because V and P, they are equal to each other and opposite, but they produce a moment. Okay? They produce a moment so that the left part of the cantilever would rotate clockwise. In order to avoid this, we must also apply a moment counterclockwise to the right face, such that this moment counterbalances exactly the moment of P and V. The symbols are not very well visible because the figure is taken from a book. So here, where I am putting the mouse, this is M. It's not very well visible. It is a symbol M, exactly like this one. Okay. So this moment is counterclockwise, and must balance exactly the action of P and V, okay? If we calculate the moment with respect to the right end of the left part of the cantilever, the moment of V with respect to it is 0 because the distance is 0. So the only moment is P times X. So the compensation of the moments must be such that the moment on this face is equal to the product P times X. Obviously, this moment and this vertical force V actually come from the other part of the cantilever, the one that is fixed to the wall, okay? So the left face of the right part of the cantilever that has been exposed after removing the other part, of course, they are subjected to a force and a moment that are equal and opposite to those that we have just calculated, okay? So the global situation of the forces and moments inside the material is calculated in this way. This calculation considers finite extensions of material, and actually the point where we have cut the cantilever was completely arbitrary. Okay, we can repeat the calculation at any point, and we can find in this way that V would be equal everywhere at each section of the cantilever, whereas the moment would be P times X, so it will depend on the position of the cut. Okay, but this is quite reasonable. Okay. In any case, we have used a finite extension because the load P is concentrated, okay? Instead, when we have a distributed load, we must consider infinitesimal portions because the load is a load per unit length, okay? And it may change from one position to another. Okay, so in the next slide, we shall see how to deal with the distributed load. And eventually we don't do it, but if we have the combination of a concentrated and distributed load, we have to do the calculation by infinitesimals, okay, as we shall do in a second, and then add the calculation with the concentrated load. Okay, now consider the case where we have a distributed load that we describe as a function Q that represents the load per unit length. So it is a force per unit length applied to the cantilever. In this case, we must extract an infinitesimal block of width equal to dx of the cantilever. And then, as usual, impose that the block is in an equilibrium condition. So, for instance, we must say that if for any reason the force acting on the left, the shear force acting on the left is pointing upwards, which is reasonable if we assume that we have used the same structure as before, okay? If we take an infinitesimal block from here, the left part will have the force the shear force pointing up, and the right part will have the shear force pointing down. So it is consistent with the other figure, okay? The two forces, V on the right and V on the left, cannot be equal because we also have Q that is pushing from top, okay? So that the action of V must be equal to the action of Q plus the action of V on the right-hand side, and V on the right-hand side must be different from V on the left, but the difference must be infinitesimal because the length of the block is infinitesimal. So we can call V the shear force on the left, then we call V plus dV the shear force on the right. dV may be positive or negative. In this case, as we shall see, dV will be negative. And then we shall add the action of the distributed force on top. So we have that V, if we take the orientation upwards as positive, we have V in the equation. Then Q is oriented downwards, and the contribution from Q is infinitesimal. It is Q times dx because Q is force per unit length. And then again with the minus, because V plus dV is pointing down, we must subtract V plus dV, okay? Conclusion, all this combination of forces must be equal to 0 because of the equilibrium condition. So it follows that V and V cancel, and we have dV over dx equal to minus Q. Okay, Q may depend on X. Okay, it's not necessarily a constant. Okay, it depends on the form of the load. Okay. So this is sufficient to calculate the shear force at any position in the structure because Q of X supposedly is prescribed. So it is some function that we know. So we simply, V is the primitive of Q, okay? Then we must repeat the analysis for the moments in order to prevent rotation. So also in this case, as you can see in the figure, the moment on the right is not necessarily equal to the moment on the left because we have also the moment produced by Q, okay? To calculate the moment, we need an origin. And for instance, we may take the origin for the calculation of the moment produced by Q on the left face of the block. Okay. So to calculate the moment we must produce by Q, we must take Q times dx, that is the force, and then multiply the force by again dx. Okay, so it is like integrating Q 2 times. Okay, so the slide will not change, only the bottom part of the slide will change. Now you can see the balance condition for the moments. Okay, we have the concentrated moments that are m. So we take we agree that the moments that are counterclockwise are positive. Okay, so m plus dm, you can see it at the end of the formula, is positive. whereas m on the left is negative. Okay, so these are concentrated moments. Simply minus m, the one on the left, m plus dm, the one on the right. Okay. Then we have the moments produced by the shear forces. They also produce a moment. It is the same like in the example of the concentrated forces. We had P times X, and then there was V times 0 because V was in the origin, okay? In this case, the shear force pointing upwards, that is on the left face, contributes nothing to the moment because we have taken the origin on the left face. So it is like V times 0. Instead, V plus dV contributes to the moment because it is at the distance dx from the origin. So we must calculate V plus dV times dx. This is clockwise, so it takes a minus. So we have, as you see, minus parenthesis V plus dV parenthesis dx. And then we have the second integral of Q that is also clockwise, so it is negative, and makes minus q dx over 2. However, we have different orders of infinitesimal quantities because you see immediately that minus m compensates m, okay? So there are no finite terms in this equation. Then we have dm, that is infinitesimal of the first order. Then we have minus v dx, that is also infinitesimal of the first order, so they stay. And then we have dv dx, that is second order, so we eliminate it. And the same is for dx dx times q. Okay, so actually, along an infinitesimal block of material, the effect of q is of the second order. So the only terms that survive are minus v dx plus dm equal to 0. That makes dm over dx equal to v. Okay. This does not mean that q is non-effective, because if you remember from the previous calculation, we had v is the primitive of q, and now we have m is the primitive of v, so it is the second primitive of q. So actually the moment is the second primitive of q that has an effect on the moment as well as should be. Okay, so we have the possibility to calculate also for the distributed load, okay, the value of the shear force and moment at each position in the cantilever. One may argue, is there any component of the force parallel to the cantilever? The answer is obviously no, because there is no load with a component parallel to the cantilever. However, it could be, okay? If you consider this figure, the load P3 is not vertical. So this load has actually two components. One component is vertical and can be treated in the same way as we did before. And the other component is horizontal, but the horizontal component is absorbed completely by, is compensated by a force that comes from the block in this figure on the left. Okay, so we do have also a horizontal component of the force inside the cantilever. So the cantilever is also expected to deform horizontally. Okay, so if P, the component of P3 pushes to the left, the cantilever will become shorter. Okay, but in a situation like this, the deformation along the axis is less important, is of higher order than the bending of the cantilever. Okay, but actually, if the loads have two components, then there will be also an axial component of the stress inside the cantilever. This slide simply describes the way we take the signs, but it is not important for what we want to say. Now we come to the plates. So this figure, the lower part of the figure, is a replica of the figure that we started considering at the beginning. Okay, but the other part is the top view of the device. So you can see that the rectangular region that is indicated here with the dashed thick line is actually the area in which the silicon has been made thinner and thinner in order to have the plate, okay, or the membrane. Okay, the two sides are thick, and also the lateral parts along the y direction are thick. Okay, so we have a membrane or a plate inside a much larger structure. Okay, so first of all, we can assume that the much larger structure is able to block any motion of the boundaries of the plate. So this plate is blocked at the boundaries. Okay, it is essentially a two-dimensional structure because we neglect what happens in the z direction that is normal to the plate. Okay, we assume that there will be no relevant phenomena related to the third direction. Okay, so we must consider only what happens along the x and y axis. Okay, the theory of the plate is not easy. We are not going to develop any theory of the plate. Okay, so one important theory to describe the behavior of a plate under a distributed load is due to Kirchhoff. Okay, but I'm not going to work out the equation or the solution of the equations. I just want to show you some simulation results relating to a plate made of silicon. Okay. The theory of Kirchhoff assumes, as we already anticipated, that the lateral dimensions of the plate are much larger than the thickness. Okay. Okay. So this is a simulation of the displacement in the vertical direction, that is in the z direction, of a plate made of silicon. the quantities are normalized. So instead of having X and Y, you may see it along the horizontal axis of the figure. It says distance X bar equal to X divided by the length, okay? So it is X bar is a normalized coordinate, okay? That is the actual coordinate divided by the length along the X direction, okay? Another issue is that if the plate is subjected to a uniform load, or actually, as you may see in the figure that is upper left, there is some pressure on the upper face that is called P2, and another pressure different from P2 that is called P1 on the lower face of the plate. But P2 is uniform with respect to X and Y. It's constant everywhere. P1 is also constant. It is just a different constant with respect to P2, okay? So the plate is subjected to a difference in pressure. But since these pressures are uniform, by reasons of symmetry, it is sufficient to consider only 1/4 of the structure, okay? So the 1/4 of the structure that has been considered is the one indicated with the red lines here, in which the origin is in the center, okay? So the normalized abscissa X goes from 0, that is the center, to the edge, and the edge is, of course, 1/2, because it is normalized. And similarly, the other coordinate Y goes again, it is normalized to the vertical side of the membrane, goes again from 0 to 1/2, okay? So in the figure that is on the right, what is shown is the displacement in the vertical direction, also normalized, okay? As a function of X, so going from 0, where I'm pointing the mouse right now, to the edge, to the boundary. Obviously, at the boundary, there is no displacement because the structure is the membrane is blocked at the boundary. And the red lines show a replica of the simulation at different positions related to Y. And they are shown in the figure. So for instance, you see that Y bar equal to 0 is this line here, exactly the line that is in the center, in which Y normalized is equal to 0. The next one is 0.1, the second red line from top. The third one is 0.2, etc., etc. 0.4 here, and then there is no 0.5 because 0.5 is the boundary, and at the boundary nothing moves. So the displacement at the boundary is obviously equal to 0, okay? This comes from a numerical solution of the two-dimensional problem of the plate according to the Kirchhoff theory, okay? The issue is, at any position of the plate, we can calculate the deformation, okay? And then we can connect the deformation with the stress of the material at each position inside. These are other details, but they refer to the same analysis. So this file was over, so I must now put the next file on the screen. Just a second. Here we are. Okay, so it's just a continuation. Okay, and now we start with some applications. And as I anticipated, a reasonable application of the cantilever concept is that of considering the cantilever as one of the two plates of a capacitor. Okay. So if we start from the standard expression of the parallel plate, the capacitance of the parallel plate capacitor, we observe that in the undeformed situation, the capacitance that we call C0, zero stands for the undeformed situation, okay, when there is no deformation of the cantilever. Obviously, the capacitance is given by the vacuum capacitance permittivity, sorry, epsilon 0 times the relative permittivity of the dielectric times the area of the capacitor divided by the distance of the by the thickness of the dielectric. Okay. Obviously, in this case, dielectric is air because we must be able to obtain a structure that moves, okay, up and down to change the capacitance. We can put together all the parameters. So the area is fixed and the permittivities are also fixed, okay? So the parameter that may be able to change is the distance d between the plates. So we write C0 as the equivalent permittivity that incorporates also the area divided by the distance, okay? So how can we obtain a capacitor in which one of the plates moves? Well, one example is a primitive example, of course, is in the part, the lower part of the figure. We may have a lower part in which there is the metal electrode that is fixed, the one in which the caption is metal counter electrode, okay? And then we have the upper electrode that is called the silicon movable electrode, okay? And this electron must be able to move. And in order to be able to move, it must be attached to the rest of the structure with a very weak piece of material so that it is able to move. So silicon spring is just a piece of silicon that is very thin, okay? So it can be deformed elastically by some external force. If that happens, the upper electrode will go closer to the lower electrode, okay, and the capacitance will increase, and vice versa, okay? So this is a primitive description. We can do much better. And first of all, the idea is, why should we use 2 plates? Why don't we use 3 plates? Okay. If we use 3 plates, such that the upper plate is fixed, the position of the upper plate is fixed, and that the lower plate is also fixed, and the middle plate can move up and down, okay? Then if it moves down, it will increase the lower capacitance, and at the same time it will increase the, will increase the lower and decrease the upper capacitance, and vice versa, okay? So with this arrangement, we obtain a structure in which substantially we double the sensitivity of the device, okay? So let's try to make some calculations. Let's call with D as before the distance, the common value of the distances of the middle plate with respect to the upper plate and the lower plate when the structure is unperturbed, okay? So when the structure is unperturbed, the middle electrode is equidistant from the other 2 electrodes, and the distance, the common value of the distance is D. Then we indicate with X the variation of the distance with respect to D. So if we indicate, for instance, with C1, the capacitance between the middle electron and the lower electron, and we assume that the distance is some D plus X. So X is positive, so the middle plate has gone up, okay? Then we have the lower capacitance C1 will be equal to the equivalent permittivity divided by D plus X. And if we neglect higher order terms, this can be written as C0 minus delta C. Okay. So of course, when X is positive, so if the middle plate goes up, the lower capacitance decreases by some amount delta C. The upper capacitance C2 makes just the opposite. So it will become C0 plus delta C. So if we succeed in making a differential measurement, so in a way that we can detect the difference between the 2 capacitances, we obtain a quantity that is 2 delta C equal to, when we sum up all these results, we have 2 times the equivalent permittivity times X divided by D squared minus X squared. So this is important because the differential measurement eliminates the background, okay? Delta C may be very small with respect to C0. Okay, so measuring C1 alone, that is C0 minus delta C, okay, may have a lot of noise in it because we have to measure a variation of something with respect to something else that is big. Okay. When we perform the differential measurement, we eliminate C0. Okay. So we measure just the variation. Also, we can manipulate the equation. We divide by 2 everywhere. And then we assume that the displacement x of the mid plate is not so large to the point that we can neglect x squared in the formula. So if we neglect x squared, we obtain that x is equal to d squared times delta C divided by the equivalent permittivity. But on the other hand, the equivalent permittivity over D is just C0. Okay? Conclusion, by measuring delta C, we measure X. So we measure a displacement by measuring a capacitance. Okay? Then the origin of this displacement may be different. Okay, we may have different external reasons for this displacement, and we may apply this idea to the measurement of different types of displacements. Let's see. Sorry. So this is an example of the application of the concept that we just discussed to measuring accelerations. Okay, this is, for instance, applied into the airbag systems of cars. Okay, there is just a couple of minutes left, so I just anticipate the explanation. If there is a crash, of course, the car will undergo a sudden acceleration. So we may exploit the acceleration in order to have the middle plate of the capacitor that we discussed before, to have it moving from the equilibrium position. Okay? And in that case, the displacement will be produced by an acceleration. Okay? So we are measuring the acceleration if the acceleration is larger than some threshold, then the airbag will go off. Okay? So in order to describe the structure, it takes time, so it is better that for the moment we stop, and we shall start again in 10 minutes. Okay, so we'll start. We were on this figure here, in which if you look at the left part of the figure, you see that in the lower part there are structures that are indicated as fixed outer plates. So the upper and lower plate of the capacitor of the calculation that we have done before. Now the figure has been rotated by 90 degrees. So the upper plate is on the left and the lower plate is on the right. Their positions are fixed. The black dots, the little black squares visible in the figure indicate anchors, meaning locations in which the rest of the structure is firmly blocked. Okay, so the fixed outer plates are blocked forever in their positions, and in the situation that is described by the left part of the figure, the center plate is equidistant. So there are two capacitances that are indicated as CS1, CS2 in the figure that are equal to each other. Also in the inset above, you can see that there is again the structure of the two capacitances. The center plate is attached to a thick bar that is called beam, and the beam is attached to the anchors, to 4 anchors, by very thin beams, okay, that are indicated with the name tether, okay. So the tethers are very thin, so they can bend if there is some external force, for instance. Now, what happens in this device when there is an acceleration in the horizontal direction? So that the acceleration, if you look at the right part of the figure, the acceleration is to the left, okay? So the beam is massive. Instead, the tethers are elastic. So the tethers will deflect. And due to the acceleration, the beam will be, we start right, okay? So it is like if you are in a car and the car has a crash, like a sudden stop on the right, the acceleration is negative, so it points to the left, and the beam will, by inertia, will go to the right. This will produce a change in the distances between the plates, so the capacitances, the capacitances will change. Okay, how do we implement such a thing? It is visible in this figure. Of course, why should we just take two capacitances? We can take many, okay? So in this case, the structure is rotated by 90 degrees with respect to the previous figure. So you can see all the upper and lower plates the upper plates are gray, the lower plates are black, and the moving plates are in between. Okay, so there are like 8 structures like this in the upper part of the device and 4 more structures in the lower part. Okay, it is interesting to see how the bar, the mass that is indicated here as shuttle motion, okay, that can move vertically. How is this mass attached to the anchors? There are actually 2 anchors, one on top and the other on the bottom. And you see the two structures called folded spring. So the folded spring is a thin boundary of semiconductor material. It's just the boundary of a rectangle. Inside where it is white, it is empty, okay? So this is a very thin structure, okay? And if there is an acceleration in the vertical direction, the upper spring will be compressed or extended, and the lower one will be extended or compressed. Okay, so of course, having many capacitances will provide a much better signal, okay, to be detected. This is a picture of the actual structure. The movable plates are those that appear darker, okay? And this is the beam. And the fixed plates are this one, this one, this one, and so on. So how do we measure the signal? Okay, so if you look at the upper left part of the figure, you see that the spring, the mass has accelerated upwards. So the spring that is attached to the upper anchor is compressed, okay, and the lower one is extended, okay. So because of this, the middle plate has gone up, okay, and the 2 capacitances have become different. Now, let's look at the circuit, okay. Assume that we apply a voltage V0 on the upper capacitors and the voltage minus V0 on the lower capacitors. Okay? And then we detect the voltage in the middle plate, okay, Vx. We start from a symmetric situation, okay, in which the 2 voltage drops, V0 minus Vx, and respectively Vx plus V0 on the bottom, are equal to each other, okay? And then we assume that the relation between the force and the acceleration is linear. Sorry, the force and the deformation of the spring is linear, okay? You remember that in the calculations that we performed at the beginning, the motion, the extent of the motion of the middle plate was indicated with x. So x equal to 0 means the unperturbed situation. X different from 0 means that the situation is perturbed, okay? So if you assume a linear dependence, and we call K sub S the constant of the spring is the combination of the upper and lower springs here. We have that the force corresponding to some deformation X is, apart from the sign, that depends also on the direction in which there is the motion, apart from the sign, the force is proportional to the elongation X, that is the displacement of the middle plate with respect to the unperturbed position, okay? Now, if you consider this circuit, you find immediately this relation, okay? Why? Because the total charge in the middle electrode cannot change because we are detecting Vx with an infinite impedance equipment, like, for instance, the gate of an MOS transistor. So the charge that is stored in this electrode can never change, okay? It may modify in the sense that the total charge may distribute between C2 and C1, okay? But globally, the middle electrode is neutral, okay? If there is a charge in the lower plate of C2, there will be an opposite charge on the upper plate of C1 and vice versa, okay? So we can impose the equality of the charges on the two capacitors, C2 and C1, and write that the two charges are equal. On the other hand, the charge in the upper capacitor is V0 minus Vx times the capacitance. So it is the voltage drop times the capacitance. And the charge in the lower capacitor is Vx plus V0 times the capacitance C1. So they must be equal, so we extract this relation here. This relation is the equation that describes the equality of the charges on the plates of these capacitors. Okay. Then we extract Vx. Okay. Vx comes about to be V0 times C2 minus C1 divided by C2 plus C1. So you remember we calculated the difference of the capacitors, okay? It is here. The difference delta C of the capacitors is proportional to X, okay? So we can replace delta C with this formula, and in the denominator we can replace this sum with 2 times C0 because they differ very little with respect to C0. In the numerator we have the difference, so C0 is eliminated, but in the denominator it is not, okay? So in this way we have a relation between the measured voltage of the middle plate and the displacement X of the middle plate. On the other hand, the displacement is related to the force by the relation that you can see in the middle of the screen. Fx is equal to Ks times X, apart from the sign. So the force is equal to the product of the mass times the acceleration. And this, of course, is the acceleration of the beam and the mass of the beam. So if we replace the force there and then we divide by the mass, we see immediately that the acceleration is proportional to the elongation, x. And the elongation is proportional, due to the formula that we calculated a minute ago, to the measured voltage of the middle of the middle plate. So eventually we have that measuring Vx is equivalent to measuring the acceleration. Okay? In the practical cases, the voltages V0 and minus V0 are not continuous. They are pulses, as you can see in this figure here. Okay? And then if there is a displacement of the plate, Vx will also have the form of pulses, as you can see in the red line here in the figure. Okay, but then it is adjusted electronically. So what we obtain at the end by some circuit is a signal that is constant with respect to time and different from zero. So this is a signal that is eventually proportional to the acceleration. Okay, so this is how the accelerometers work. Now we go to the other effect. Instead of using the change in a capacitance due to the mechanical deformation, we exploit the piezoelectric effect. The piezoelectric effect is the formation of an extra voltage due to a distribution of charge that in some materials is a consequence of the application of a mechanical pressure. Okay. There is also the inverse piezoelectric effect, in which the application of a voltage will give rise to internal forces in the material. Okay. The mathematical description is similar. Okay, we also, we shall see it in a minute, we have to deal with some tensor whose structure is the same as that we examined before. And the upper part of the figure is a qualitative description of the effect. Essentially, consider a capacitor. Okay, so we have a capacitor in which the dielectric has a thickness equal to some h, and the area of the plate is some A. Then we are able to measure the voltage between the two plates of the capacitor, and at some point we apply some force to the material. What happens qualitatively is the following. Assume that you are able to determine the charge that is called delta Q inside the material, or the variation of the charge due to application of the force. You remember from the Gauss theorem that the charge in the volume can be found by integrating the displacement vector d over the surface. Okay, so in this case it will be the displacement vector d times the area. Okay, then this displacement vector, if there is a piezoelectric effect, is proportional to the mechanical stress sigma. So in the formula, sigma is the mechanical stress. And D is some coefficient that relates the displacement vector capital D to sigma. So D is some parameter, okay? It's not a differential, okay? On the other hand, sigma is a force per unit area, so sigma times A is a force, and this is the force that in this example is applied normal to the plates of the capacitor, okay? On the other hand, the variation of charge induced by the piezoelectric effect is also related to a variation in the voltage across the device, because if I take the variation in the voltage and multiply it by the capacitance of the capacitor, I obtain the variation in the charge. So the variation in the voltage is equal to the variation in the charge that is given by dF from the above formula divided by the capacitance, that is of course equal to the permittivity times the area divided by the thickness, okay? So F over A is sigma. So in conclusion, due to the piezoelectric effect, we produce an extra voltage between the two plates that is equal to some coefficient d, small d, times the thickness of the device times the stress in the normal direction divided by the permittivity. Oh, this is just a qualitative thing, okay? That shows that if there is a piezoelectric effect in the material, then we have a relation that connects the displacement vector to the mechanical stress, okay? Then we have to use the general description of the phenomenon. And the general description of the phenomenon is indicated in the formula below, in which you see there are many indices, okay? So sometimes when there is a sum over indices, the symbol of the sum is omitted. So you see that di on the left-hand side, di is any of the three components of the displacement vector, is given by a term that is of the form epsilon. Epsilon is a permittivity, but it is in tensor form. If the material is anisotropic, then permittivity will have different components, okay? And it is multiplied, so the permittivity tensor is multiplied by the vector E, that is the electric field. So it is implied that we have a sum, a symbol of sum that is not written, over K from 1 to 3, okay? So it is assumed that if there are repeated indices, then there is a sum implied. Then there is another term that is dikl times sigma kl, in which sigma in itself is the stress, so it is a tensor by itself. So the coefficient D must have three indices. One is I, that is the index of the component of the displacement vector, and KL are the other two indices over which we have to sum. So in the second term, there is a double sum over K and over L. Okay, so this is the general expression of the displacement vector for a material that is, first of all, an isotropic, so that the permittivity is not a scalar, and second, that has the piezoelectric effect, in which the displacement vector is also influenced by the mechanical stress. Now, for typical materials that could be used as dielectrics for these applications, okay, like silicon dioxide or barium titanide or zinc oxide, as you see in the table. Permittivity is a diagonal tensor, in which it also happens that the first two elements are equal to each other. For silicon, they're almost equal, all three of them, okay? So the behavior of silicon dioxide is practically that of a scalar material, okay? This is for the permittivity. And then we have the other coefficient, in which, as you remember, the stress tensor sigma is symmetric. So there are only 6 terms that are independent out of 9, and they can be arranged as a single vector, okay? So if we manipulate sigma to become a single vector, we need only one index that goes from 1 to 6, and we call this index M. And for this reason, also the coefficient D, instead of having 3 indices, will have 2 indices, I and M. And it must be a matrix that is made of 3 rows. Each row is 6 element long, okay? So that the multiplication of D by sigma will give you a vector with 3 components, okay? So this is the form of D in general, but for the materials of interest, D simplifies very much because many of the elements are equal to 0. For instance, in silicon dioxide, there are actually 2 independent elements. That's D11 and D14, and then D12 is non-zero, but it is equal to D11. And then there are 2 more elements that are non-zero in the second line and none in the third line, okay? For the other 2 materials, the situation is similar. There are just a total of 5 non-zero elements, but only 3 of them are independent. So there are 3 different values possible, okay? How do we measure these coefficients? Well, we simply apply the stress independently to each direction at a time. Okay, so obviously in these figures the orientation of the electric field will always be vertical, because the electric field will appear across the two plates that are indicated in blue, and this is the only thing that we can measure. Okay, so we can measure that electric field and correspondingly the variation with respect of the charge. Okay, but we can change the direction of the stress. For instance, we can apply the stress, as we can see in the upper part of the figure, vertically. Okay, so in that case we are considering zinc oxide. We measure D33 in the first measurement. Instead, if we apply the stress transversally, as you can see in the bottom part of the figure, we measure D31. How can we exploit this effect? Well, again, we must build up a structure that is able to deform. Okay, so you can see a structure like this is a structure in which first we started from an aluminum support, that is the black area below. Then we built up a device. You see that we have a drain, contact. We have a P+ well in the material. So essentially there is a structure of a transistor. Okay, there is the region that is indicated with polysilicon is of course a gate. Okay, but then on top of the structure, but below the metallization of the gate, there is a deposition of zinc oxide. That is the thick gray area that is in the middle of the structure. Okay, then in order to allow the structure to bend, much of the aluminum support that was underneath the device has been removed by a suitable chemical attack. Okay, so the all this structure has become a cantilever. Okay, or a micro beam, how it is called here. Okay, if there is, this is an accelerometer. If there is an acceleration, the microbeam will bend. In the zinc oxide, there will be some extra mechanical stress. This will produce an electric field, or a difference in voltage with respect to the unperturbed condition. And this variation in the voltage will affect the gate voltage of the MOS transistor. So the current in the MOS transistor will change because of the variation of the gate voltage. Okay, so this is another possible method to obtain an accelerometer, different from that we examined before using the capacitors. This is just the same thing, in which the equivalent circuit of the device is shown. Here we indicate the capacitance produced by the layer of zinc oxide, okay? But this layer is piezoelectric, so it will be able to provide, under deformation, the difference in the voltage across it. And this will, of course, I mean, Vs is a given bias. Vd is a given bias, okay? If we change this voltage, we modify the gate voltage of the transistor, and we expect a current flowing through the transistor. You see, this is a depletion mode transistor, okay? Because of this white dot here. This is another implementation. This is a different application of the piezoelectric effect, in which they have realized the touch sensing devices. Okay, so those devices that when you touch them with the finger, because of the change in the voltage of the capacitance, they are able to modify the signal or the current inside an MOS transistor. Okay, so the principle is the same, the device is different, so the structure of it is shown in the next couple of slides. You see here that there are that the gate is sandwiched. Okay, we have an MOS transistor with an N channel. Okay, then we have a standard gate insulator and the metal here. And then we have another layer, and this material is a polymer. And then we have another gate on top. Okay, so the polymer has the piezoelectric effect. So it will be able to provide a change in the voltage under pressure, okay? And if one touches, there will be a pressure here indicated with force, and again, we shall have a change in the current of the transistor. This is just the same structure with more details. In particular, if you look at the three color picture that are on the right, okay, here you have the red parts are the source and drain N plus diffusions. The blue part is the P substrate. Okay. Then there is the oxide layer. These two things are the contacts for the drain and source. The light blue is another insulator. In the middle, we have the gate metallization. So it is this one, the intermediate metal that is on the left figure. Okay. Then they put the polymer on top, is the green region. Then, of course, there is the deposition is over the full area, but it is then removed. And then the top of the polymer gets another metallization. So the intermediate gate is floating, okay? It's a floating gate. And by exerting a pressure on the top metallization, we impose to the polymer to provide an extra voltage, and this extra voltage will reflect into the floating gate, and from this into the channel. Okay, so the current, this device is called MOSFET, that likely comes from pressure MOSFET. Okay, they call it MOSFET. It is quite linear. This is a diagram of the applied force on the horizontal axis with the output voltage on the vertical one. And then we now consider another, or we start, because there are not so many minutes left, we start considering another type of sensor, still based on the piezoresistive or piezoelectric effect, but in this case it is called piezoresistive. It is again a piezoelectric effect in which the parameter that changes due to the application of an external force is the resistance, or actually the resistivity of the material. And this is something that is, for instance, typical of silicon. Okay. So let's see why we expect that in a material like silicon, we experience a variation in resistivity due to the application of a pressure. Okay. For that, I need some old slides that I showed you several hours ago, so let me try to find them. Okay, you should be able to see a slide showing the bands, the valence and conduction bands of silicon, germanium, and gallium arsenide. Okay, consider silicon. That is the central part of this figure. Silicon, you remember, has 6 minima in the conduction band, and they are aligned 2 by 2 along the 1, 0, 0, 0, 1, 0, and 0, 0, 1 directions. Okay. In this figure, only one is visible because the left part of each figure is related to the 1, 1, 1 direction. Okay. Another figure that you may remember is this. So this figure shows the surfaces of equal energy of the conduction band for silicon, gallium arsenide, and germanium. Consider silicon. And you see that the surfaces of equal energy are ellipsoids of rotation. That means that two of the axes are equal and one axis is different. And you may remember that the two axes that are equal are associated to the transverse mass of the mass tensor of silicon, and the other one, the other axis of the ellipsoid, that is the longitudinal one, is associated to the longitudinal mass. And if you remember the numerical data, you also remember that the transversal masses in silicon are considerably smaller than the longitudinal mass. Now, you also remember that in order to describe the dynamics of the electrons of silicon, we describe the relation between force and acceleration using a scalar mass that we call the transport equivalent or effective mass. And this mass is a combination of the transversal and longitudinal masses. Okay? This mass also provides the inertia of the electron under the application of the external force. So qualitatively, we expect that if we are able to have a small effective mass, we shall get more current because the inertia of the electrons under the application of a field will be small, okay? If the electrons are heavy, then we shall get a lower current under the application of the external field. That means that the resistivity will be larger, okay? Conclusion, qualitatively, we may conclude that the resistivity for a single minimum of the conduction band depends on the values of the transversal mass and the longitudinal mass. When we consider all the minima all together, well, then there is a combination of these values, so we make an average, okay? So silicon is anisotropic near each individual minimum of the conduction band, but it becomes isotropic when we combine all the effective masses of the minima together. Now, if we have a mechanical stress in one direction, the material becomes anisotropic again. So there will be one direction privileged and two directions non-privileged, or vice versa, okay? So it may happen that by suitably applying a stress, we privilege the motion of the electrons whose masses is transversal. So we will get more current, or maybe we'll get a smaller resistivity, okay? Whereas if we privilege the electrons whose mass is the longitudinal one, that is heavier, then we expect to have less current or a larger resistivity, okay? So this is a purely qualitative analysis, but it shows that possibly by controlling the stress in one or the other direction. If we succeed by this, and we do because there is the piezoelectric or piezoresistive effect, in privileging some groups of electrons having the lighter or the heavier mass, we can control the conductivity of the material. Now we stop because it is already 6:30 and we shall continue on this subject on Tuesday. Thank you.